Hello, this is Temis Gouliakis, and I'm going to talk about optimal testing of discrete distributions with high probability. This is joint work with Elias Diakonikolas, Daniel Kane, John Peebles, and Eric Price. Let's start by defining what is property testing and for probability distributions. So the type of problems posed in this area can be summarized in the following questions. You're given a set of samples from a discrete distribution over a domain from 1 to n, or it can be a k-tuple of such distributions. Can we distinguish with probability at least one minus delta whether this distribution or k-tuple belongs to a certain class of distributions P from it being epsilon far from any distribution in this class? So the class is also called a property, and hence the name property testing, and the algorithm is called property tester. This field was originally introduced more than 20 years ago by Goldreich and Ron and Batu et al. In 2000. Another more interesting question to computer scientists is the following. So what is the smallest number of samples that's sufficient to perform such a task? This distinguish between distribution being in P versus being epsilon far from P. And more specifically, we would like to know what are the relevant parameters that we should express such a sample complexity as a function of. So let's now move on to define the two main problems that we will talk about in this talk. So the first one is closeness testing. In this setting, we have two probability distributions, P and Q, over the same domain 1 through n. Our algorithm, the property tester, is given samples from each of these two distributions, say k samples, and the goal is to output accept when the samples from are equal, and output reject if these distributions are at least epsilon far apart from each other in total variation distance. And also the confidence parameter is 1 over delta for an arbitrary delta. And by confidence, we mean that these guarantees need to hold with probability at least 1 minus delta. Similarly, the problem of independence testing is the following. So suppose that we have a distribution P, which is a joint probability distribution now over a two-dimensional domain n by n, which let's say has marginals P1 and P2. So in this problem, the tester is getting k samples from the joint distribution P, or in other words, you can think of it as getting k samples from each of the marginals P1 and P2. And again, the goal is to output accept when the probability P is equal to the product of its marginals, and reject when these distributions P and the product of its marginals are at least epsilon far apart from each other. And again, we have we want to solve this for an arbitrary confidence delta, or in other words, an arbitrary error probability, an arbitrary confidence 1 minus delta, which means that our error probability delta is also arbitrary. And speaking of the error probability, up until very recently, the entire literature in this area was focused on proving upper and lower bounds in the constant confidence regime. So that means when the error probability is constant, like usually 1/3, but it doesn't really matter. So for closeness testing, the state of the art, the upper and lower bound is, as you can see here, theta of n to the 2/3 over epsilon to the 4/3 plus square root n over epsilon squared samples, and this is due to 10 Diakonikolas valiant and valiant. And for independence testing, the bound is n to the 2/3, m to the 1/3 times n to the 1/3 over epsilon to the 4/3, plus square root of n times m over epsilon squared. and this bound is due to Diagon-Nicolas and Kane. So as I said, this is for constant error probability delta. So what happens when we want to boost this confidence? We want an arbitrary error probability that can be close to zero. So in this case, the only thing that was known until recently is that we can use sort of a technique that's reminiscent of BUP amplification, which is essentially you repeat the test log 1 over delta many times, and using like a majority vote, you can you can decide either to accept or reject, and the accuracy of this or the error probability of this is going to be delta if you have repeated log 1 over delta times. So obviously that adds another factor of log 1 over delta in sample complexity, which turns out to be suboptimal. It's also obvious that in these if someone wants to improve on this naive bound, you need new ideas and algorithms, at least for the two problems that I described in this talk. So can we do better? So for the problem of uniformity testing, there has been some work along these lines, and the best now the optimal bound is now known, and the optimal bound that includes all three relevant parameters: domain size n, the proximity parameter epsilon, and the error probability delta. And this bound for uniformity is square root n times square root log 1 over delta over epsilon squared plus log 1 over delta over epsilon squared, where with the naive amplification, that would be square root n over epsilon squared times log 1 over delta outside the square root. As you can see from this bound, the number of samples remains sublinear even for error probability as small as 2 to the minus n, which would not be the case with the naive approach. So this bound is due to a paper by Diagon-Nicolas et al. And also, I should mention that this apart from uniformity, this also works for identity testing using a non-reduction by Goldreich. So now for closeness and dependence testing, that's the topic of this talk. There is a recent work by Kimball, Chris, and Wasserman that does break the barrier of naive amplification, but it's still not optimal in the sample complexity, the upper bound that they get. We now come to the main contribution of this work, which is to prove both upper and lower bounds. So tight bounds of these two probabilities of closeness and independence testing that you can see on this slide. So this settles the sample complexity for these problems for all three types of parameters: the domain size, proximity parameter, and error probability. Let's move on to see some details of our approach for closeness testing. Suppose that you have xi and yi to be the histogram, as we call it, of distributions P of a sample set that's taken from distribution P and Q respectively. So xi and wi are random variables that denote the number of times each element I is sampled when S samples are drawn. So each of these random variables is represent as a value in the histogram. One idea someone can think about is define the following statistic. In particular, to take the sum of the absolute differences of these values and sum for all domain elements. and hope that this is a good statistic that will help solve the problem. I'm going to take a step back here and state that so it's very common in this type of problems that we define a good statistic and hoping that it will have some nice properties. So what are these nice properties that in expectation this will separate our completeness case to the soundness case. So the completeness case is the case where in this example the two distributions are equal, p is equal to q. The soundness case is when the total variation distance between the two distributions is at least epsilon. So our goal would be to find a statistic that in expectation is very far apart in the two cases, and it also has good concentration. So by setting a threshold, we can output like accept if the statistic is below the threshold, or reject if it's above it. So what is the problem with this particular choice of statistic that I mentioned? So the problem here is that the expectation of this statistic heavily depends on P and Q, on distributions P and Q, even in the completeness case, even if they are equal. So for example, imagine that P and Q are Bernoulli random variables, probability 1/2 versus probability 99%. So the value of this statistic is going to be much larger probability 1/2 than it is at 99%, and this actually makes it possible to create instances where having two distributions equal to each other versus a bit far from each other is very hard to distinguish. So in order to overcome these issues, we define a similar but slightly different statistic by using more copies, like more sets of samples. So a second set of samples from each distribution. So as you can see in this formula here, we have apart from xi, yi, we also have xi prime and yi prime. And we designed this statistic in such a way so that we ensure that the expectation will be 0, and this will be 0 for any pair of distributions in the completeness case. So for any distribution P and Q which are equal. So it's not that important that it's 0, but what's important is that it's consistent, that it is the same in all instances in the completeness case. So what is the idea here? As I said, we need to show that there is a large enough expectation gap between the two cases. So the expectation of Z when we're in the completeness case has to be, we said it's 0, but where in the soundness case, you have to show that this expectation will be large enough, and also that we have a large enough concentration of this random variable Z in both of the cases. So this will enable us to choose a threshold in a certain way so that we can satisfy all the requirements that we want. Okay, so let's see what is the algorithm more precisely. We first set the value k to this quantity, which is basically the sample complexity that we're aiming for. So we draw this many samples, and we will split them into 4 multisets uniformly and independently. So we draw an independent random variable, uniform like probability 1/4 for each of the sets, and split the samples in this way. And then we create these 4 sets. Like for each element I, we create an xi, yi, xi prime, yi prime. We compute the statistic zi as we discussed earlier, and And our final statistic Z is going to be the sum of all Zi's. So when this sum of all Zi's is at least a constant times square root of k log 1 over delta, we will output accept, otherwise we output reject. And now let's see why. Let's give some intuition why this would work. As I said earlier, the first thing we need to do is to prove an expectation gap. In other words, suppose that this statistic idea is just defined. We already know that, as we said in the completeness case, its expectation is 0. So what we need to show is for the soundness case. So if P and Q have total variation at least epsilon, then the expectation of Z will be large enough. And in our case, like for the threshold that we have chosen, large enough is omega of square root k log 1 over delta. To give you some small idea on how the proof goes, suppose that we draw k samples, k as defined in the algorithm. One thing we can show is that for all domain elements I, the following is true: that the expectation of Zi is at least the minimum of one of these three terms. K Pi minus K Qi, so Pi and Qi are the probability mass assigned to this element by distribution P and Q respectively, or these other terms. And so the main idea in the proof that is once you have proven this claim, it suffices to show that the bound on the expectation of Z holds for each of the three terms. And why is that? The reason is that if you have P and Q with total variation at least epsilon, then and you have this claim, then this means that there exists a subset of the domain that the contribution of at least one of these three terms to the total variation distance is at least epsilon over 3. So so this is linear in epsilon, and so if we can show that for each of the three terms the bound holds, then we're done. Okay, now regarding the consideration of the statistic Z, recall that it's easy to see from the definition of the statistic that this is two Lipschitz. So if we change, if only one of the samples changes, the value of Z can only differ by 2. Can only change by 2. So because of this, we can apply McDermott's inequality, a well-known consideration bound, and get that the probability that Z deviates more than this much from the expectation, more than square root k log 1 over delta, can be bounded by delta, essentially by something order of delta. So that would complete the proof that our closeness tester with this particular sample complexity works. Now regarding the independence testing problem, to give you some intuition on what our approach is. So in this case, one idea would be that we can use our closeness tester in order to do this. So why is that? Because the independence testing problem is equivalent to a closeness testing problem between the joint distribution P and distribution Q, which is defined as a product of P's marginals. Okay, so Px and Py are the marginals of P. And we can actually use the closeness tester because we can simulate samples from distribution Q using twice as many samples from distribution P. How is that? We can get 2 samples from P and then choose the first coordinate of the first sample and the second coordinate of the second sample to simulate the sample from Q, from product of the marginals. However, unfortunately, this does not give the optimal bound because one term that is n times m to the 2/3 would appear, while, as we said, we need n to the 2/3 times m to the 1/3 when n is the larger of the coordinates. The idea that we use in order to fix this issue comes from paper by Nicholas and Kane from 2016, and this idea is that we're going to flatten both coordinates of the domain before doing the testing. So what does flattening mean? It means that each domain element of this of the domain n by m is going to be split into sub-elements, and and samples from one of the elements are now assigned to the sub-elements that that domain element has been split into. Okay, and this the intuition why this is beneficial to us is that if we have more signature samples, so this would create more singleton samples in the domain. And if you recall how the statistic is defined, the singleton samples don't contribute anything to the variance of the statistic Z. So this allows us to prove even stronger concentration bounds and for Z, so that we can improve the in turn we can improve the sample complexity bound. And another crucial idea in the proof is that samples. So we need to use samples both for the flattening phase and for the testing phase of the algorithm. And in order to guarantee that our requirements will be met, so we cannot guarantee that in one go, but if we reassign our samples like constantly many times, so we reuse the same sample set and we reassign them to either each sample to either flattening or testing sample, and if we do this multiple times, eventually our requirements will be met. So to conclude, in this talk, I described, in this paper, we described the first sample optimal tester for closeness independence, which works in the entire parameter range, and for all 3 relevant parameters, which is the domain size n, the proximity parameter epsilon, and the error probability delta. In the paper, we also saw matching lower bounds by extending by information theoretical, extending the information theoretical analysis in Diakonikoulas and Kane by using KL divergence in addition. And finally, we also obtain tight upper bounds, so both upper and lower bounds, for the following 2 additional problems. Testing closeness for a collection of distributions. You have m distributions, and you want to see if each one of them is close to a specific distribution. The other problem is closeness testing of distributions, but with an unequal number of samples for each of them. And another way to think about this is that so this is basically an interpolation between independence testing and closeness testing. So if you had vastly greater, if you had an infinite number of samples from one of the distributions, it's equivalent to knowing this exactly. So this is the independence testing problem. Thank you very much for your time, and I hope to see you in the poster.